Okay, so over the last few weeks, we've been studying computability properties, functions on real numbers and sets of real numbers, leading up to some quite abstract and perhaps even difficult material, especially last week and the week before. So if one's crudely classifying the different material in this course into easy, medium, and hard, I would put the last 2 weeks in the hard bracket. And this topic is computing with infinite data. Line here. So today, which is 7th of December, we're going to have an introduction to that. And so we're beginning a new topic, and it's going to be about computability using a new kind of Turing machine. So I'm going to view this as a kind of bit of breathing space in the course, if you like. We're going from hard material, again, if we're making a crude classification of the difficulty of material into easy, medium, and hard, then today is going back into the easy bracket. And this topic is going to occupy us really for the rest of the course, but the main focus on it's going to be over the next 3 weeks leading up to the Christmas break. So we are going to have 2 more lectures after today before the Christmas break. So the last lecture before Christmas is going to be on the 21st of December. And where we're going to get to is the application of this to computing with real numbers, which is something of practical use. Well, really computability of functions on real numbers. And this is, by the time we get to the end of it, this is no longer easy difficulty, but in the crude classification, this one's only medium difficulty. However, as a bridge between these two, in the middle week, next week, we're going to look at some important aspect of computing with infinite data, which is there's a topological aspect of it. So we're going to involve some topology, but hopefully most of you know a bit of topology. If you don't, all the definitions will be given, but people that know some topology will have an advantage. Let's call it topological aspects of. And the main material next week is also going to be of medium difficulty. So the break for the break with the easy material is just for this week. But also next week, the second half of the lecture is going to be, while we're doing topological aspects, we might as well do it thoroughly. So there's going to be some more challenging material in the second half of the lecture next week. So we're going to have sort of cover the full spectrum. And I haven't completely decided how I'm going to do the oral exams yet for this course, but I think part of it's going to be based on some of the topics from the lectures will be labeled as hard topics, and you can choose in an oral exam if you want to go for a hard topic or not. But if you want to go for a 10 on the course, then you will have to choose. You will have to choose one of the hard. Well, you'll have to elect to be to be able to answer one of the hard topics. Okay. Anyway, so for today we're going to be able to relax a bit and look at a new model of computation, and hopefully nothing is going to be very difficult today. Maybe I just want to So are there any questions on this before we carry on? We are being recorded, just to emphasize in case you want to ask questions, being recorded. Right, so what do we mean by computing with infinite data? Well, so far in the course, we've been looking at computing, like deciding, computing functions on finite data. So far we've looked at finite data. And such things include natural numbers. A natural number is a finite object. And the general model we had of computation at the beginning was computing with words over an alphabet. The alphabets were finite, and every word is, of course, finite because it just has finitely many characters in it. Words over an alphabet. And we also use representations as ways of representing more esoterical mathematical things, such as even computable functions themselves, as finite objects via codes for them. So either words or natural numbers that coded them. So now we're going to look instead at infinite data. And what sort of infinite data might we be interested in? So are we interested in? Well, I've already said here we're going to look, what we're working towards in this part of the course is looking at notions of computability for functions of real numbers. And so one of our main and motivating examples of infinite data is going to be a real number. You might think, well, real numbers, they're very finite things. I mean, a real number represents a finite distance. But the point is, we want to think of real numbers as being given to us. How can we compute real numbers exactly, so to speak? And if you're computing a real number exactly, you need to be able to approximate it to infinite precision. So you need an infinite amount of discrete information to give a real number. Just the familiar decimal notation for a number like pi, well, it's an infinite sequence, and you can't get away with any finite sequence for it. And just as before, we're going to approach computing with abstract entities like numbers via representations of them as concrete entities that our machines can deal with. And the idea of representing a real number as an infinite sequence of digits already suggests kind of an ideal model of what infinite data a machine might be able to compute with, and that's an infinite word, an infinite string or an infinite word or a stream, if you like, of symbols. So in fact, our main machine model today is going to be looking at, it's going to be Turing machines computing with infinite words over an alphabet. Right, so just to say, I don't know how many of you looked at it, but at the start of the course, I put Turing's original paper, which he defined his Turing machine model, and he gave his solution to Hilbert's Entscheidungsproblem in that paper. And you might have noticed that in that paper, rather than considering as the primary study for computability notions of decidability, semi-decidable, and computable function, which is what we've been focusing on so far in the course, because nowadays people tend to focus on those aspects. Actually, Turing's main question that he was answering was, what is a computable real number? In fact, the title of his paper was on computable numbers, and by that he meant real numbers. So already in Turing's paper, we had the notion of what it means for a real number to be computable. Turing, 1936, already introduced notion of a computable real number. And what it means roughly, well, even precisely, but I mean, one can make this precise, is that one has a Turing machine which will produce the decimal expansion of the number. That's a correct definition of computable real number, and Turing's definition is pretty much that definition. And namely, a real number which a Turing machine, I'll just write TM, can produce the infinite decimal representation. Of course, some real numbers have two different infinite decimal representations. All such numbers are rational numbers of a particular kind. The rational has to have a power of 10 for the denominator. I think, well, it has to be expressible with the power of 10 as denominator. But if it's rational, of course, it's computable because there's a pattern to it anyway. So D is not really too bad a use of the English article, definite article here. Produce the infinite decimal expansion. Well, what do we mean by producing the infinite decimal expansion? Well, imagine your Turing machine has several tapes, and one of them we designate as the output tape, and we require the Turing machine to write the real number onto the output tape. So, for example, the number pi is computable because there are several well-known algorithms for computing the digits of pi. It's kind of nowadays considered as a good test for high-performance computing models. So there's actually quite a bit of competition computing as many digits as pi as possible in the high-performance computing world. But anyway, we certainly have algorithms that we can use on a low-performance Turing machine, and the Turing machine will produce the digits of pi. So 3 might ask it to put the decimal point in the right place, and so this is what the Turing machine outputs on the tape. And so we can perfectly well, we don't need a new Turing machine model to define the notion of computable real number. But the actual definition is a little bit awkward. Because what do we actually want to ask it to do? Well, we want to be able to run the machine for infinite time, and eventually we're going to have pi left on the output tape. But that's actually not enough. Because suppose we ran the machine and we got 3.1415928. 7, 4 or something like that. We could, we could perfectly well have a computation that goes like that, and the machine computes a bit further, and then it goes and overwrites the last 3 digits that were wrong, and then starts the right digits. Starts with the right digits. So if all we require is that eventually after infinite time we have pi on the tape, then at any finite point in time, we actually don't have any information because we don't know whether that information would be overwritten later. So the definition's a little bit fiddly because we need to make the stipulation. I mean, it's not a difficult thing to do. We need to make the stipulation that once we've written the output, we don't overwrite the output. It's only a little bit awkward. That we never overwrite the output. So we require that the Turing machine only ever outputs a digit on its output tape when it knows that it's correctly computed the next digit. Okay, so I mean, we can perfectly well make this definition, and that's okay. So we could do this notion of computable real number with Turing machines. But actually, something else we would like to do is have potentially know what it means to be able to compute functions on real numbers, where the real number as the input to the function might be given as an infinite stream by some other machine that's computing its infinite streams. So obviously you view these infinite streams as something that you can always ask for some more information if you want it. And then we go and compute, and we want to then produce some output into the output stream. And now we're getting, things are getting a bit more complicated with the Turing machine model, because in addition to this fiddly aspect of not overwriting the output, we now have to start explaining how a Turing machine is going to deal with an infinite input and also deal with an infinite output. Now you can model those concerns directly using Turing machines. There's time, I'll say a little bit about that at the end of the lecture today. If not, there's something in the notes. But the more natural thing to do is to just say, well, if we want to do this, we want to actually consider these streams of numbers and streams of infinite words, as we're calling them, so the stream of symbols as data, as input data and output data. Why don't we tweak the definition of machine? Tweak means modify a little bit. Tweak the definition of Turing machine so that it deals directly with such things. And that's what we're going to do. So it's a small modification, but it's useful for this purpose of studying computability on infinite data. So smoothly deal with computability on infinite words. We shall adjust the notion Turing machines to build this feature in. So it's not necessary. We could do everything using ordinary Turing machines with appropriately slightly more complicated definitions, but I think this approach is natural, and it gives us an excuse to have this breather in the schedule and look at a new computability model in doing so. So this leads what are called type 2 Turing machines. I think in the notes I just call these T2Ms, type 2 machines. So before giving an actual example and then the definition of the type 2 Turing machine, well, that was very out of focus, so there's a focused bit on this anyway. I'll leave that focus there in the video while So this week there's nobody on Zoom, so there's nobody to tell me when things go out of focus. So before looking at the notion of machine, let's actually consider a very simple example of how one might compute a function on infinite words. I just want to check my notes just to see if I missed anything out. So let's consider how we might compute a function on real numbers if they're given as infinite sequences of digits. So example of computing. Yes, I did indeed. Thank you. Forget to move the camera. I was going to do it before, but then I realized that it was out of focus. So thank you very much. For example of computing a simple function. So let's suppose our input is just a sequence of decimal digits so that we can understand what's going on. So I'll forget, I won't have a decimal point, and I'll view such a sequence of digits as representing a number in the closed interval between 0 and 1. Okay, so 1 would be 9999999, 0 would be 00000, and let's assume the input, doesn't matter what the input is for the algorithm because the input should work, the algorithm should work for any input, but let's assume the input is the decimal part, the fractional part of pi once 3 is taken away. And the algorithm, this is the sort of thing we should be able to do. It's a really simple algorithm. Algorithm is consider the next digit, the next input digit, input digit A, and output 9 minus A. So I mean, this is really silly, but anyway, so first input digit is 1, so we output 9 minus 1, which is 8. The second input digit 4, so we output 9 minus 4, which is 5, 8, 4, 0, 7, 6. Oh, sorry, 9 minus 6 is 3, and so on. This is obviously the sort of thing we should be able to have an algorithm to do. You can imagine that one would like to do much more complicated algorithms than this. But still, we want a machine model that's going to give us this sort of capability. The important thing is it's an algorithm, so at any point, you can have looked at some finite portion of the input, but you can never look at the whole input. Okay, whenever you're going to output something, you must have done finitely many steps before, so you can have looked at sort of an arbitrary finite portion of it. Here we were doing it one digit by digit, but in general we might look at quite a lot of digits in order to output the next digit. So this is an algorithm that maps infinite sequences of decimal digits, numbers between 0 and 9, to int. So any such infinite sequence of decimal digits gets mapped to an infinite sequence of decimal digits. But this algorithm also computes a function on real numbers. We view, as I say, an infinite sequence of digits as representing a real number in the closed interval 0, 1. So this algorithm computes the function. Well, so if x is the input number, what's the output number? 1 minus. Yeah, very good. So compute the function 1 minus x. Something to ponder about And this was actually a mistake in Turing's paper, which he corrected in a follow-up short note. Something to ponder about is the notion of function you get in this way using the decimal representation is a bit restrictive. So try and think about this, but there is no way using this representation of multiplying a number by 3. I mean, obviously, multiply by 3, well, if it's greater than the third, then you would cut it off at 1. But there's no way of multiplying a number by 3. So you might try and you can multiply by 2, I think. Anyway, but you certainly can't multiply by 3. Well, I'll have to think about multiplying by 2. I'm not sure. Anyway, it has its limitations, and we'll come to that in 2 lectures' time and solve it. But for the moment, we're going to really consider mainly today the task of computing functions on infinite words. So the idea of a type 2 Turing machine is it's going to be a natural model for algorithms that take input infinite words and map them to output infinite words. So what does a type 2 Turing machine look like? A type 2 Turing machine. Well, such things are not really very established in the literature. So my definition, I've chosen it in order to be close to the text, like one of the main textbooks that deals with these, which is the book that's referenced on the course web page called Computable Analysis by Klaus Weyrauch. It's very dry in how it's written, but nonetheless, if you want to look more details, you can have a look at that book. My definition is not exactly the same, but it's quite close to what he does. The point is, we want to give inputs that are infinite sequences, kind of given as streams. We need to do some computation, and to do some computation, we will need some working space. And we want to output, and with the output, we want the restriction that I've already mentioned, that we never overwrite something that we've already output. So to model that in a nice way, I'm going to ask for some specific input tapes. So we're going to have K input tapes. Hang on, let me just check that. Yes, it is K input tapes in the notes. So the input tapes, they're going to contain infinite sequences, so they're only going to be infinite in one direction, because you have a starting sequence. So here are the K input tapes. And each of these contains a word, an infinite word from the input alphabet. I'm not going to write everything on the board because we don't want to clutter it, but I'll give the formal definitions a bit later. And the point of the input tapes, they're only for input. Put the dots here. So each of these has its head, and these are read heads. From an input tape, you can read, but you don't need to write. Each with a read head. And also with the read heads, it's enough to let them go in one direction, because we're going to have some working space anyway. So if we need to remember something we've read, we can write it into the working space. If we don't need to read it, like in the algorithm we were looking at here, we didn't need to remember anything, we just work locally, then that's fine, we don't need to. Right, so the triangle here means a read head, and the arrow means it only moves to the right. Then we have some working tapes, so we'll allow, I'll use capital N for these, so N working tapes. And these are like the tapes of an ordinary Turing machine, as we've been using. So these are going to be infinite in both directions. You know, they don't have to be. That was part of what we discussed when we were talking about variations of Turing machines earlier. They don't have to be infinite in both directions, but it's quite convenient for them to be infinite in both directions, because then you can always make sense of moving left and moving right without having to worry about dropping off the end. So each working tape has these are ordinary Turing machine tapes, so you have heads that can both read and write. So I'm going to mark these as half black triangles. Well, sorry, it's half blue. I'm using a blue pen. Yeah. Anyway, kind of thinking of it as half of it as a sort of erasing. It's like a pen nib with a pencil nib with an erasing part and a writing part, a pencil lead. And these, just like ordinary Turing machines, these can move in both directions. So each with read-write head. Then we have the output tape, which is where we're going to write our output. And once again, we want the output to be an infinite sequence. So there's no point having a left part to the tape. We're going to just write a start at the start and write in one direction. And now the output tape, infinite in one direction, and it just has a write head. The only thing you can do is write. Again, if you need to remember what you've written for later, you can record it on one of the working tapes. And again, we don't want to ever overwrite something that we've already written, so we make sure that when we've written something, we move to the right. So again, this is a unidirectional head. It only moves in one direction. So one output tape with a write head. And in addition to that, so it's very much like a Turing machine. You've just got these special input and output tapes with the heads that work in appropriate ways. And in addition to that, we have, as with an ordinary Turing machine, a finite set of states, and the machine configuration at any point can be in a particular state. So we have the machine configuration is in some state. Okay, so let's consider an actual example of such a Turing machine. This is really like the stuff from the first lecture when we looked at some very simple Turing machines. The only slight drawback about using the type 2 Turing machines is that Daverin and I are not aware of any type 2 Turing machine simulator online. So unfortunately, you can't have an exercise class of programming type 2 Turing machines into a simulator. Maybe that could be a student project for somebody. It'd be more like an undergraduate project rather than a master's project. So let's right, so we're going to consider, just before the break, an example type 2 Turing machine. And to make it very simple, this type 2 Turing machine is going to have just one input tape and no working tapes. It doesn't need, like the previous algorithm I described, the one for 1 minus a real number x, this Turing machine doesn't need any working space. it's going to be so simple. So the input tape here, when it starts computing, we assume it has some input on it, an infinite amount. So I suppose we've got 1, 0, 1, 1, 0, 1, 0, 0, 1, 0, 0, 0, 1, and so on. So we're going to have an input-output alphabet, which is 0, 1, and a tape alphabet, which also contains the blank symbol, which is never the input tape never contains the blank symbol. We always assume we're given an infinite input. And the output tape, well, it starts off blank, and the right head is at the left end of the output tape, and the read head starts off at the left end of the input tape, and of course we start in the start state. And let's give the instructions, and in doing so, I'll a little bit explain what the format of the instructions for a type 2 Turing machine is. Very similar to the Turing machine. So this says if we're in the start state, I'm going to use semicolons to separate out the main fields here. So we're going to have something to do with start tapes, something to do with the input tapes, something to do with the working tapes. So to do with the input tapes, we've only got one input tape, and this is if we're in the start state, and we can see a 0 on the input tape. And then we need something for the working tape, so all the symbols we can see on the working tapes, but there aren't any. I'm just putting the semicolon in to emphasize that in general, for type 2 Turing machine, there would be a field of what we do looking at the working tapes here. So this, if we're in the start state and we see a 0 on the input tape, then we go into a copy state. We move the read head, which can only move right or stay where it is. We move it 1. We don't do anything with the working tapes. Must admit, I'm a bit confused what this second semicolon is. I just need to step forward with my notes to. Aha, right. Yes. So this field would be for what we write on the working tapes, and this field would be for the edge displacements on the working tapes, but both of those are empty because we don't have any working tapes. And the blank symbol is for what we do with the output tape, which will, hang on, is that the right one? Which is right. But in any case, this is not a very interesting instruction for us because we're in the start state and we can see a 1. So we don't fire this instruction. The interesting instruction is what we do if we're in the start state and we see a 1. Well, in this case, we go into a new state 1s. We don't move the input head at all. We have nothing to write and no movement to do on the working tapes because there aren't any, and we write 1 onto the output tape. So let's do that. So we've seen the 1 here. So we go to install, let's see a 1, so we go to state 1s. We write 0. Sorry, yes, sorry, this 0 means, I'll put a plus 0. This means don't move the read head, and we write 1 onto the output tape, and whenever we write onto the output tape, the head automatically moves to the right. Okay, because we're committing to we always commit to what we've written on the output tape. Now we're in state 1s and we see a 1. And when we're in state 1s and we see a 1 on the input tape, then we stay in state ones. We keep the input, the read head where it is. We don't do anything on the working tape, and we write another one on the output tape. So now in ones we see a 1. We don't do anything on the read tape. We write another one on the output tape, and we move to the right. We're still in state ones. We write another one on the output tape and move to the right. We're still in state ones. We write another one on the output tape and move to the right. And you can see that basically we're going to fill the output tape with the infinite sequence of ones in this case. Okay. So let's just record that. So on input 1 0 1 0 0 1 0 0 0 1 and so on, the output is 1 1 1 1 1, just the infinite sequence. So we'll write this as 1 to the omega, infinite repetition of 1s. Okay, so let me just illustrate this machine that I had in mind on slightly different input, where this time we do start the input with 0. So it's the same, continues the same as before, but the first input now is 0, so we've got the read head here. So now we start in the start state. You see the 0, so we go into the copy state. We now this time we didn't move the read head last time. This time we do move the read head 1 to the right, and we go into the copy state. And now we have this blank for what we do on the output tape, and the blank means keep the current square. We've got the right head there. Keep the current square blank and keep the head in that position, waiting because we're not yet ready to commit to an output. Okay, so now we're in the copy state, seeing the 1. So when we're in the copy state, looking at a 1, then we stay in the copy state. We move the read head 1 to the right, and we output the 1 to the output tape. So copies to the 1. So we stay in the copy state, we move the read head 1 to the right, we output the 1 to the output tape, and of course the output head moves automatically move to the right as we output a symbol. Now we're in the copy state, seeing a 0 on the input tape. If we're in the copy state and we see a 0, well, you might have guessed because the name of copy plus 1. So again, we stay in the copy state, we move the read head 1 to the right, and we output 0. I should say actually this example machine is not in the LaTeX notes. So the LaTeX notes has all the theory and stuff, but doesn't have the example. You can copy it down during the break if you haven't already. I should have said that before. So now we're in the copy state, we copy the 0, and we move the right head to the right. We're now still in the copy state, we stay in the copy. We have to move the read head to the right. Instead, we're in the copy state, so we copy the 1, we move the read head to the right, the output head to the right. We see the 0, we're still in the copy state, we copy the 0, move the read head to the right, the output head to the right. And so this is what we did on input 1 0 1 0 0 1 0 0 0 1. So on input 0 1 0 1 0 0 1 0 0 0 1, the output is we basically just notch the 0 off the front and put it right. A very simple algorithm that has this kind of dichotomy in its behavior, depending on whether the first symbol is a 1 or the first symbol is a 0. Right, so it's pretty much 3 o'clock, so we will have to break until 3:15. Something for you to think about during the break is we can think of these infinite sequences as giving a real number in the interval 0, 1 in binary notation, an infinite binary expansion of a real number. What function does this Turing machine compute on viewing it as a function on real numbers between 0 and 1? Okay, we've got 15 minutes to think that over. We start again at 15:15. Right, so we have the notion of this two Turing machine and this one very simple example machine that doesn't have any working tapes and does something really simple. So I asked you a question about it, but I don't want the answer to the question yet. I want to just say, before we think about what function on real does this compute, a priori, this has nothing to do with the function on real numbers. A priori, it's a Turing machine that's computing an operation on infinite words. And you can see from the way it's defined, it will always, whatever the input sequence, it will always output an infinite words. So it really does define a function on infinite words. Computes the following function on infinite words. So we'll assume that the input word P, so again, following this class of biographic books that I mentioned, which anyone who's interested can try and find a copy of that. But the input word, I use P as my typical letter for infinite words. So P is an infinite word, and my mathematical notation for the set of infinite words over set is going to be that set to the omega. Just think of it as a countable power of the set 0, 1. So an element of this set is going to be an infinite sequence of 0s and 1s. And in the background part of the notes, the lecture notes, there's the introductory bit on notation. There's a bit there about the notation I use in this course for infinite words, but I'll introduce it. I'll introduce that notation as I go along. So anyway, it computes the following function given an input word P. The Turing machine, as hopefully most of you have noticed, we have the, depending on whether the